Hi, everyone. Okay, so light is absolutely necessary for life on Earth. The second thing that is most necessary on Earth in order for life to occur is water. And so we're going to talk about water and how the interaction between light, which creates temperature, and precipitation then starts to influence climate or creates our climate. So let's start on that next. All right, so temperature. We started to talk a little bit about this when we were talking about light, but I think it's really important to connect the dots that when light is hitting the Earth and is hitting directly at a 90-degree angle or a very high angle, that means that a single photon is hitting a single small area of space, like that bullet analogy, and therefore has a higher amount of energy per square unit of area compared to when light is hitting on a low angle and therefore is being spread over a greater area. So not only does that change the quality of light in those two locations at any given time, but it also changes the amount of temperature because as infrared energy is arriving on Earth, we then change the temperature of those spaces. So this is all to say that temperature is going to change as we change the way that the sun is hitting the Earth, the angle that it's hitting the Earth. So it depends on which time of year it is as to what temperature that particular location is because the sun is hitting at different angles. And that is exactly the story. Now, when we start looking, it's kind of fascinating to look at the temperature in any given location because the range in temperatures can vary dramatically in some places and very little in other places. And we call this a latitudinal pattern. So the latitudinal pattern is basically solar heating decreases away from the equator when sunlight is spread across larger areas in the winter, so when that tilt is pointing away from the sun. The interesting thing is, however, that even though the sun is sending out the same number of photons across all the different spaces, the temperature at 30 degrees north is not going to be the same as the temperature at 30 degrees south. And even accounting for time of year. And that's because there are different amounts of land masses in those spaces, and land versus water absorbs and reflects temperature or photons in different ways. So what we end up seeing is a broader range of temperatures at 60 degrees north than we see at 60 degrees south, simply because of the amount of land mass that is there. I think it's also interesting to see that temperatures at the equator stay very constant. They're always warm, but they're very constant, whereas the range of temperatures at the poles is greater. But this uneven heating is not simply because the tilt isn't quite the same or something like that. It's actually because the tilt is exactly the same in both directions. It's because there are different amounts of land masses. And of course, Europe and Asia take up a huge amount of space, as well as North America, a huge amount of space in the northern hemisphere, whereas in the southern hemisphere, the continents of South America and Africa and Australia take up less amount of physical space. Okay, so how does precipitation arrive? Well, this is totally related to heating and temperature. So this is why we're building towards precipitation from temperature. As you know, hot air rises, right? So solar heating of all the air on Earth causes air to rise. And what happens next, so we get this hot air rising, and then what happens is as it rises, it cools down. It gets really cold. And so right around here, it starts to rain a lot. It rains and rains and rains and loses moisture through condensation processes. You've learned about these in chemistry and physics. This is where it relates to ecology and biology. So as the temperature then, because it's cold air falls, so that cold air will fall, and as it's falling, it warms back up again. When it warms back up again, all of a sudden what it does is it's drying out stuff. It dries out the land below it because it's basically this big space that can be absorbing lots of moisture. So there's lots of evaporation and evapotranspiration occurring in this location. Here's the wet areas, here's the dry areas. So it evaporates water, and then so by the time it gets over here, it's full of water again. We call this circular process a Hadley cell. And Hadley cells, there are 6 of them on the Earth, and they span a 30-degree latitude. So when we start to look across the Earth, the dry spaces, the deserts occur at 30 degrees, and the tropical rainforests, where there's lots of rain, they occur at 0 degrees latitude. It's kind of fascinating. So we start to see this whole process developing where we can see patterns of really wet areas and really dry areas because of this phenomenon, the Hadley cell. I think it's important to start noticing, if you can see on the right-hand side of the slide, that temperature influences how much water can be held in a cloud. And so you can see why, even in places where they might be on the wet side of a Hadley cell, if the temperature on average is cold, it can't hold a lot of water. So there is some variation between Hadley cells as to how much water is included in them, but the wettest Hadley cells always are found in very warm environments. Okay, so here is how the Hadley cells lay out on the globe. You can see 6 of them. They're continuous circles around the globe, and essentially there's one that ends in the tundra. Remember, the tundra is very dry and starts in the temperate forest, which is quite wet. There's another one that has the temperate forest as its wet space, and you can see they sort of go in opposite circles. They're not traveling in exactly the same way. But so there's the water, the wet area of one. They're mirror images, I guess is what I want to say. So then it ends in the deserts at 30 degrees north and 30 degrees south, right? And then there's another Hadley cell that ends up at the tropical rainforest in the middle of the world, which is super wet. So you can see here another illustration of a Hadley cell. You can see that as this Hadley cell is traveling across land, it picks up water. It picks up humid water. It's nice and warm air. That warm air collects water. As the hot air rises, it drops that water, allows for precipitation in fairly limited ranges, right? And then that cool, dry air then falls and evaporates more water in places where we find deserts. So the sun, this all occurs revolving around 0 degrees latitude. What's interesting is depending on what you call the equator. So the equator can be defined as 0 degrees latitude. It can also be described as the solar equator, which is where the sun hits the earth on a 90-degree angle. And that can, of course, be dependent on tilt. So it can vary between 23 degrees north and 23 degrees south, depending on what time of year it is. So that's what a Hadley cell looks like. And so when we start to look at this seasonal approach to where the sun is, how the earth is tilting, you can start to see that the solar equator dramatically varies at depending on the time of year. At March and September, the equator is the equator at 0 degrees. But at the December solstice and the June solstice, because the Earth is tilting, we end up seeing the solar equator vary. So that in June, the solar equator is 23.5 degrees north, and in the in December, the solar equator is 23.5 degrees south. Kind of cool. So the equator, if we're talking about the solar equator, varies quite a bit. Now, what's interesting is that we also see patterns of rainfall across longitude. So it's not simply that there's only these bands of wetness that occur, like rain that occurs latitudinally, but we also see similar patterns across longitude. And essentially what happens is we will have when water is warmed over the ocean, it's warmed over the ocean, it's very humid. As it's warmed, it starts to rise, especially when it's forced up to rise by a coastal range, by a mountain range. When that happens, we end up seeing a lot of rain right at the place where it's being forced up. So on the ocean side of the mountain range. Of course, after the clouds have rained themselves out, they move across here and the air is cool and dry. It will fall and it will evaporate. And so we have what we often call the rain shadows on the non-coastal side of a range. We then may also see that coastal wind may pick up more rain. Sometimes it's wet enough that there's enough rain all through here. You can see that this is all green. It will continue to pick up more moisture, again, be forced up by a cascade range, so a very large mountainous range, and you can imagine the Rocky Mountains being a cascade range. It will force that air up. It will dry itself out even more because it's higher and therefore losing more humidity. And on the lee side of the cascade, we will see a dry area called and that is the major rain shadow. This will be a minor rain shadow over here, but largely fine because water will be running down. In this case, there is no more water left. There's no more humidity left in this cold, dry air. And so this area will be very low on moisture. So here's a picture of British Columbia where we have both coastal hills as well as Cascade Mountain. And you can see this is a picture of the annual mean precipitation or average precipitation in locations. And what you can see is significant amounts of rain that happens all along here. There's even slightly less on these spaces right here. So if you start to think about what you know of British Columbia and its terrain, and maybe you know very little, so feel free to stop this video and go and look at some pictures of the terrain of British Columbia. But if you look at Vancouver Island, for instance, there's a bit of a coastal range right here. There's some hills, and this area will get slightly less rain on both sides. And then, of course, there is the Rocky Mountains, which push that incoming air up and in, and therefore dries out those clouds, that air, quickly to form what we consider to be rainforests, temperate rainforests, very close to the coast. And of course, after you get across the mountain range here, what we end up seeing is very, very dry space. Now, of course, this is what a climatologist is really interested in. We are ecologists here, and what we're interested in is what on earth grows places. So what grows, I don't know if you can hear the scramble behind me, that's my cat. I'll introduce him in another video. What grows right on the coast? Well, probably plants that love a lot of rain. What grows in these sort of right on the edge where you can see yellow in these spaces? That's an interesting space to look at. And what grows out here, which is super dry, receiving only 225 to 250 millimeters per year? What grows there? Now, you may also have the fun opportunity to travel to BC, and this precipitation pattern can influence where you should go to vacation in BC. Now, do you want to go and visit a rainforest? That means you should be going to the coast. Or do you want to go to wine country and lavender fields and such? That means you need to go to the Okanagan Valley, just on the other side of the mountain range. You can see the mountains there, but this is the dry side of the mountain. What you're looking for in terms of vegetation and activities will be entirely influenced by the physical environment. And so with that, I'm going to thank you, and we'll talk some more about climate next.